Okay, so let's continue with this problem, and we look at this generic element denoted by uh, defined by two nodes, ith node left side node and jth node right hand side node, and the coordinates, the nodes are identified by the coordinates xi and xj, and the interpolation function corresponding to node I and node j, they can be either derived from first principles, or we can use Lagrangian interpolation formula, and the respective interpolation functions are obtained as first degree polynomial, as you can see. And we also compute the derivative. Uh, the other day somebody asked how do we take care of the derivative function if in the computer program. So this is how you do. I mean, you know the function to begin with, and if you know the function, you can also compute the derivative. Now you can encode this expression as a derivative expression, and wherever you need derivative, you use this expression for the derivative. So let us now look at the problem that we had. So let us first look at a problem where this entire length is defined by only one element. Right? Okay, so let us not talk of so we have this node. The entire domain is discretized, or the finite element, only one element is used to define the entire domain. Right? So omega is identical with omega 1. We can do that. So if we do that, then what is the weighted residual statement? W minus dw by dx so xi to xj q by l, l minus x boundary term. So let's not worry about these boundary residuals. Boundary residuals will be taken care of at the stage of algebraic equations. Right? So boundary conditions to be imposed on algebraic equations after assembly. In this case, there is no assembly because we are only looking at one element. So one element that will take care of the entire domain. So W can be now two parts. I should have started the new page. There is no way I can actually. I'll have to repeat this.
Sir, you can also use the continuous page feature where you can just scroll down.
Oh, okay. Where is that?
Now you have to follow this, but next slide onwards, I mean, on
Okay.
next brainstorm.
Next session onwards. Okay, fine. Fine.
Or you can just copy only that part and paste it here.
Okay. I guess it's less error prone if I do it ab initio. I hope that's all. Yeah. So that's the weighted residual statement within the element, and now we choose or following Galerkin approach. Then W1 is identical with N1 or NIX, and W2 is identical with NJX, and U hat is of course equal to, within the element, is equal to UI for ith element E, Ni plus Uj Nj. So du by dx will of course be equal to ui multiplied by dni by dx. You can keep it ith element number, or in this particular case we have only one element, so we can afford to just say I and j. and we already have this Ni and Nj defined, so we can just substitute it here. So let us first say using case 1, so when we choose W is equal to Ni, then W Ni will replace W here, and this function Ni has to vanish at xj, isn't it, by definition? So this term will vanish, and this term will be evaluated, Ni will be evaluated to unity at xi. So this term will exist, and that is what we will get, Ae times du by dx at xi minus let's just say, okay, let it be xi dw by dx. So what is the derivative? dni by dx is xj divided by xj minus xi. So that is xj divided by xj minus xi multiplied by Ae times, now du by dx is this, so ui times again xj divided by xj minus xi minus uj times xi divided by xj minus xi. So dnj is equal to negative of xi by xj minus xi. So this is what you get, dx, and then this term xi xj, and w is equal to ni, and ni is given by x minus xj divided by xi minus xj. So multiplied by L minus x dx. Now all these expressions, they are simple integrals in single variable x, and they can be evaluated. This actually does not have anything, it's just a constant. All the integrand, there is no variation with respect to x, and that is just a constant value. So we can now look at it for one element discretization. Xi is equal to 0, xj is equal to L, and this becomes minus Ae du by dx at x is equal to 0 minus, what is this? So we can take this denominator out, xj minus xi is equal to L, so that would be L squared and the integrand is 0 to L xj square minus xi xj dx. Similarly, here we will have minus q naught L square So I take out xj minus xi, uh, that is equal to L, and that will be figuring out in this L square here, and negative sign is absorbed here in this negative. So this becomes x minus L multiplied by L minus x. Oh, that's interesting. I can simply just say right. Now we can evaluate the integrals. What does it yield? Xi, xj is, of course, this will vanish. Xi is equal to 0, xj is equal to L, so this will vanish, and xj square is L square, so we will get here uh, so this term will be equal to L cube and 0. There is something wrong here.
Sir,
Yes?
sir, what are we substituting for UI and UJ?
Oh, okay, fine. That's wrong. Fine. But UI will be one term here. Fine. So UI xj square minus uj xi xj dx. So is that what is let me look at this. What is this? Ni is equal to x minus xj. This is fine. Xi minus xj, and j is equal to x minus xi, xj minus xi. Dni by dx is equal to this is wrong. Dni by dx is equal to 1 by, this term gets derivative, so 1 by xj minus xi, and this is also 1, and this would be minus 1. So
Sir?
that is, yep. Yes,
Nothing, sir. It's okay. Now it's okay.
so that is what we were doing wrong. So this term would obviously change. So ui minus 1. So ui multiplied by uj minus ui multiplied by xj. So this is what the integral is, right? uj minus ui multiplied by xj. So that would be oh, again this is a problem. No xj here. So that would be just multiplied by L, and that would cancel out. So AE by L. Now that makes me breathe easy. Makes me breathe easy. That's the expression I was looking for. And this integral would lead to x cubed by 3 minus Lx square plus L square x 0 to L. So that would be L cube by 3 minus L cube plus L cube and minus 0. So this is simply q0 L cube by 3 divided by L square. So that is QL by 3. So this entire expression changes to Q0L by 3. So the equation that we have now for corresponding to first equation for W is equal to NIX is AE du by dx at x is equal to 0 minus AE by L this is of course uj minus ui, that is of course there uj minus ui plus q0 L by 3. That's the first equation, and this is equal to 0. If we now choose W is equal to Nj x, then we will have the equation here. Nj will evaluate to unity at x is equal to xj. It will vanish at x is equal to xi. So this function will, this term will evaluate to AE times du by dx. So AE times du by dx at x is equal to L minus, we will again have this AE times L square dnj by dx is 1 over xj minus xi and then again Q0 by L Nj is equal to x minus xi divided by xj minus xi multiplied by L minus x dx. So again this can be evaluated. We consider xi is equal to 0 and xj is equal to L. So this evaluates to, this one was at xj, ae du by dx at x is equal to L minus ae by L what was it, ni, did I get wrong here? What is dni? Dni is minus 1. So sorry about that. This is going to be minus 1 here. So what do we have here? Uj minus u1, so this will be minus, so this is going to be plus. Fine.
Sir,
Is that-
third term should, sir, excuse me, sir.
Yes, yes.
Yes, sir, that third term Q naught L by 3, that should have also negative sign, sir. Because we interchange in the bracket, here, sir, x minus xj. Sir, we converted into x here, yeah, into L minus x. We have taken, sir, x minus L.
X
So we
minus, this will be x minus L multiplied by x, L minus x, right? So this is what we did, but we also changed sign here. We made xi minus xj as xj minus xi.
yes.
So that would be negated. So that is fine. But this is a little puzzling. Is that? Just let me see. Okay, fine. That's okay. Yeah. So now this one will evaluate again to ae by uj minus ui divided by L. So this will evaluate to again L square, and then there would be 1L integrated of integration of this dx over 0 to L, so that 1L in the denominator will cancel out. So this L will remain in the denominator. And similarly we will have here Q0 by L square, and this is now going to be 0 to L Lx minus x square. Right. Xi is equal to 0. So this is just x, and this integral will be Lx square by 2 minus x cubed by 3. So 0 to L. So this is equal to L cubed by 2 minus L cubed by 3. So 3 minus 2 L cubed by 6. So this integral evaluates to Q naught L by 6. So this equation now is AE. du hat by dx at x is equal to L minus AE by L multiplied by uj plus AE by L multiplied by ui plus Q naught L by 6. So let us collect the terms, uh, known on one side and unknown on the other side, and I can arrange this in terms of matrix arrangement. So ui uj AE by L 1 minus 1 minus 1 1 is equal to, what do we have? First equation Q naught L by 3, second equation Q naught L by 6, plus there is this minus AE du by dx at x is equal to 0, and here it is plus AE du by dx at x is equal to L. Now this is equal to Q, the boundary condition, isn't it? A times du by dx at x is equal to L is equal to Q. So we impose that, and the equation that we are now dealing with is 1 minus 1 minus 1 1 ui uj, or I can just say u1 u2 is equal to Q naught L by 3 minus AE du by dx. I could as well write this as reaction R Q naught L by 6 plus Q. So this is the equation to be solved for, and when we solve for this equation, how do we solve for this equation? U1 is to be imposed a boundary condition, that is U1 is equal to 0. That's the other boundary, essential boundary condition. At x is equal to 0, displacement has to be 0. So U1, that is the node that is corresponding to position x is equal to 0. So constraint boundary condition U1 has to be equal to 0. So how do we impose that? We will do that as AE by L 1 plus alpha minus 1 minus 1 1 U1 U2 is equal to Q naught L by 3, let's just say reaction, plus alpha times U1 star, and second one is Q0 L by 6 plus Q. Right? Now U star is the prescribed boundary condition. It can be anything. Prescribed value of U at x is equal to 0. U star 1. So in this case it is equal to 0, so this term in the present case u1 star is equal to 0. So if you do that, then this of course vanishes and you are left with this equation AE by L. Alpha is of course of the order of, or not of the order of, we can just say alpha is equal to AE by L. Oh, AE by L is anyway out, 10 raised to the power 4. So AE by L 1 plus alpha minus 1 minus 1 1 u1 u2 is equal to q naught L by 3 plus R q naught L by 6 plus q. This term would vanish because u1 star is equal to 0. So alpha times u1 star is always of course going to be 0. Otherwise, if u1 star was something else, then this first equation would approximately equal to alpha times u1 is equal to alpha times u1 star, because of this alpha being very large in comparison with all other terms in the equation. So now we can solve this system of equations and find out u2, and u2 will evaluate to and u1 will evaluate to 0 approximately. So the approximation u hat x can be now written as, what was the original approximation? u1 n1 plus u2 n2. So this one will of course vanish. u2 is L by AE, q naught L by 6 plus q multiplied by, what is n2? X minus xi, xi is 0, x divided by L. This vanishes. So this is simply 1 over AE q naught L by 6 plus q multiplied by x. So this is the approximation, and the axial thrust is of course given by AE times du by dx, and that is equal to constant QL by 6 plus q. That's the solution, one element solution. Now compare how this varies, how this compares with the exact solution that we had computed couple of slides back. This one. This is the exact solution, cubic variation. Now if you plot this, and you can plot the other function, and it would be instructive how it looks like. So let's just to make the plotting simple, let us just assume everything to be unity. right? So this is, if this is true, if this is assumed, then u hat is simply equal to, and we can also assume L also equal to 1. So 1 by 6 plus 1, so that is going to be 7 by 6 uh, x, and AE times du by dx, okay, is equal to 1 by 6 plus 1, so again 7 by 6, so that is of course follows from here. And exact solution, if we substitute these values all to be equal to 1, then we will find what do we get. Let us just try to plot it. Let me see. Minus 1 by 6 multiplied by 3x square minus x cube plus 1 by 2, so 1.5x. Dx is equal to minus 0.5 multiplied by 2x minus x square plus 1.5, and UA x is equal to 7x by 6 Okay, so let us see how the approximation looks like. This is the true variation. Ux, oh, Ux is this one. Fine. Ux is the blue line, and that is what it varies. And UA is the approximation that we have. Right? It goes from 0, straight line, 7x by 6. So this is what the approximation looks like. And it will be, I mean, you can see that true solution is of course cubic, but even first degree approximation is not that bad approximation. So you can get a reasonably good trend even with using one element, and that too with only first degree approximation of the variable. And obviously the difference is going to be very stark if the approximation is not going to be as good in case of uh, the axial thrust. So axial thrust is of course varying like this, and it is, oh sorry, it's ranging from set this range 0 to 1. Yeah. So that was not visible. So this is what you have, 7 by 6, that is the constant axial thrust, right? Because the displacement is first degree polynomial, so the axial thrust is of course going to be constant. And actual axial thrust, the exact solution is quadratic. And that is what you get here. And it's not that bad approximation either, and it agrees towards the point where the natural boundary conditions are imposed. So at that point it of course has to agree, but the approximation becomes progressively poorer as you move away from that boundary condition or the force. And this actually gives us an idea, this difference between these two, that is taken as a criteria for this difference is going to reduce if we further subdivide the element domain. If we use two elements, then you will find that of course first degree two node interpolation, two nodes for each element, this axial thrust is going to be constant within each element. So what you will find is in element number one element it will be at this level, at another element it might be at this level. So progressively you actually uh, get better and better approximation progressively as the element size reduces. So we will try to solve the same problem in our tomorrow's lecture by using two elements and then see how the results improve. Right? That will also involve the assembly of equations, which was not there in this particular problem because we had only one element and there was no further assembly of equations from different elements required. But this serves as a another standard result that we need to preserve so that we can see what is referred to as H refinement. Refinement of the finite element mesh as you reduce the size of finite element. So H represents the size of the element. So if we reduce the element size, how the solutions change, right? And subsequently, we will also talk about P refinement, that is how the results change if I increase the degree of interpolation. And that is of course when I choose elements not just defined by two end nodes, I can also have one mid-side node or two interior nodes. So if I have one mid-side node, then there are three nodes in the element, and I can define a quadratic polynomial, second degree polynomial. So that is increasing the degree of polynomial interpolation. If I have two interior nodes and two corner nodes, then I can have a third degree polynomial variation, and that is how we will look at. We will go up to second degree, third degree it becomes little tedious. Right. So we'll stop here. Any questions?